Welcome to Real Casual Math. I'm Dr. P, and this is the first video in the new version of my numbers playlist. Now, first of all, why numbers? Well, because for most of us, numbers are our first introduction to math, and for many, kind of the only. Um, and it's also where most of the first set of pitfalls lies in terms of getting into math in the first place. Now, the first pitfall is in terms of the whole concept of mysterious, magical, special numbers, pretty formulas. Essentially, all of the aesthetic qualities of numbers that kind of just get in the way of learning what's actually happening. Few examples. First off, for the Harry Potter fans, or people who used to be Harry Potter fans, either way, 7. And that's kind of a big deal. It comes up a lot in the occult. See Isaac Newton, and also of course the whole days of the week. Take the lunar cycle, divide by 4. Oh wow, 7 days. But I mean, it's not actually magic. I mean, I hope I don't have to say that. And in a moment, I'll explain a little bit of, well, what's actually making it seem so mysterious in the first place. Now, another one that comes up a lot are the Fibonacci numbers. You start with 0 and 1, and then you just keep adding the previous two to get the next one, add the previous two to get the next one. 2 plus 3, 5, 3 plus 5, 8, 8 plus 13, 21, and so forth. And also the golden ratio, which is intricately linked to the Fibonacci numbers. And, here's one way to express it. Here's, part of the decimal expansion. And interesting thing is, like, if you divide, say, this by this, you get a number that's already pretty close to this number right here. And as we go on farther, divide the last pair of numbers, it'll get closer and closer. So there's a lot of, whoa, this turns up all over the place. Isn't it, magical and mysterious? And how is it doing that? But have you ever noticed that in all those, math engagement videos where they want to wow you and woo you and show you, like, look at all these places this shows up. You ever notice that they never really explain why? Like, what it is about this number that makes it do that? Well, and lastly, most people's favorite math formula, the special case of Euler's formula, e to the pi I plus 1 equals 0. Look at all the important math numbers showing up in one place. E, I, pi, 1, and 0. I think you can hear my voice that there's, that I'm not quite with that. All right, so let's take these one at a time. Let's start with 7, the first prime number after 5. Which is a kind of a big deal if you're a five-fingered ape. But otherwise, it's just a small prime. I mean, not much else to it. But between that and the whole moon thing and probably some other stuff, it does have a little apparent significance at least. But ultimately, it's still just a small prime. Golden ratio is actually really interesting, to be fair. Not magic though. It's what it actually is going on is something kind of similar to the number 7. Just big enough to be interesting, bigger than this, but still small enough to feel just a bit familiar. It's like it's got kind of got that sweet spot of familiarity and mystery to make it feel like something special. And the golden ratio is actually quite similar. It's just complex enough to be interesting, mysterious, and do some wild things, the properties of it, but it's still also simple enough as far as numbers go to just be ubiquitous, to show up all over the place. Now, just quick note, definition, it's it's the ratio where This number to the short side is equal to this long side, so we've added a square here to this side. So long over short is equal to long over short, um, done by extending a square. And we can express that as long, short, and we can, manipulate this equation a couple ways. One is to get this property, that's the direct way of just dividing through, where it says that the golden ratio is 1 plus its own reciprocal. Actually, a pretty interesting property right there. And we can also just multiply, cross multiply a bit, and get this over here. Now, with the Fibonacci sequence, it's really you take, to get this one, you add the previous two. And we can actually see some interesting things. So we have, the 2 here, the power of 1 here, and the power of 0 here. The form, this equals this plus this equals this plus this, the form is exactly the same. And ultimately, that's why these two things, the golden ratio and the Fibonacci sequence, are so intricately related because, well, I'd have to go a little more deeper into how recurrence relation gets solved, but this shows up here directly. Now, as for what like the whole complexity versus simplicity thing, it helps to compare it to a different recurrence relation, which is you get the next one by adding the previous one to itself. So instead of the one before that, it's just the previous one twice. So here we have previous and the one before. Here we have previous and just previous again. And that, by the way, is just doubling. So next one is just double the previous one. You double, you double, you double, you double. So it's just a simple exponential growth relationship. And this is ultimately the same kind of thing, but with a little more history. That's it, just a little more history. Not just the last one, but the last two. Otherwise, it's actually really similar to just repeated doubling. So in that sense, golden ratio is a lot like 2, but just a little spicier. And that's one of the reasons it's kind of ubiquitous. Another, well, another I'm going to have to save for the next episode because, well, it just requires a little more. It just requires a little more, and also it ties in really nicely with what I'm going to be talking about in the next episode. And finally, this one. So the first problem, jumping right into it, is that the meaning of the expression is completely hidden, which makes it, sure, pretty, I guess, but also kind of useless. And as for the whole pretty thing, well, there's a bit of a catch there, because this is sort of one of those things where I'm not 100% sure about the exact century, but European rich guys, way too much time on their hands, who just thought that the negative numbers were icky, so they just, they don't like having negative numbers. They didn't like things looking like this. But expressing it like this by moving the one over to the other side is actually way more meaningful. Second thing though is that well, there's that whole pi thing. Yeah. I mean, of all the numbers in here, I'm sure you expected that the I would be the weird one. That one's fine. I'll get more into that later. For now, I'll just say the words real and imaginary are very unhelpful because real numbers are not real and imaginary numbers are also not imaginary. They're very unhelpful words, and that's another thing I'm going to address later. But for now, just note that doubling pi to get something called tau is actually a bit nicer. And well, if we use that instead of pi over here, we get an interesting little expression, which also, by the way, gets the 1, the 0, and the I. But, just covering up this, e to the tau I equals 1 actually has a meaning. It means that one full turn, starting at 1, gets you back to 1. A full turn gets you back to where you started. This is, by the way, a half turn. We go from 1, we do a half turn, we're at -1. Which, by the way, is also literally the meaning of I squared equals -1. It's all just rotations. But for now, it's worth noting that the special form with the plus 1 equals 0 tells us nothing. And I mean, it's like someone went out of their way to make the equation less helpful. And ultimately, the takeaway of this episode should be that if we stop at like, ooh, look how, any of these, this number or this sequence of numbers is, if we just stop there, well, we've stopped before we've actually done anything. So let's not do that. Next time, another common problem with numbers, including like the so-called controversy of 0.9s repeating equaling 1. It does. I'm just going to say right now, it does. And I'm going to talk a little bit about why that seems confusing. And also more generally about what numbers are versus what numbers look like on paper, because these are not the same thing. The way a number is expressed is not the number. The expression is not the same as the identity. So that's going to be next video. See y'all then.